Have you ever wondered what it would feel like to stand at the edge of something so extreme that even time itself seems to hesitate, to slow, to question its own meaning? Well, what if there are places in the universe where the familiar rules you live by quietly fall apart, where light cannot escape, and where the future and the past begin to blur into a single, uneasy thought? You see, when we hear the words black hole, we often imagine a kind of cosmic vacuum cleaner, a dark mouth swallowing everything in sight. But that picture, comforting in its simplicity, is not quite true. A black hole is not a hole at all. It is a region of space and time so profoundly curved that matter, light, and even causality itself must follow a new, unfamiliar path. And that's the thing. These objects were once dismissed as mathematical oddities, scribbles on paper that could never exist in the real universe. Even Einstein himself, I suppose, doubted they were more than an abstract consequence of his equations. Yet here we are, in the quiet hours of the night, knowing that black holes sit at the hearts of galaxies, including our own, shaping the birth of stars and the slow evolution of cosmic structure. Perhaps that is why they haunt our imagination. They challenge our intuition about reality, about what it means for something to exist, to endure, or to end. Time near a black hole does not tick like a clock on your wall. It stretches and bends, more like a landscape you travel through, and if you were to fall toward one, your experience of the universe would diverge completely from that of someone watching safely from afar. And I find that deeply humbling, because black holes are not merely destroyers. They are also architects guiding galaxies, regulating growth, and offering us a rare glimpse of the limits of human understanding. In their darkness, we are invited to listen more carefully to the universe and to ourselves. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So let's continue. Long before black holes became headlines or images on our screens, long before detectors listened to the quiet murmurs of space-time itself, the idea was already waiting, patiently, in the human imagination. And I find that rather beautiful. You see, the notion that gravity could become so strong that even light might fail to escape did not begin with modern physics at all. It began in a world lit by candles and oil lamps, where gravity was still thought of as an invisible pull acting across empty space, and light was something almost mystical, swift and untouchable. And yet, even then, curiosity was enough to push the human mind towards something extraordinary. In the late 18th century, there were thinkers who dared to ask unsettling questions. What if gravity had no upper limit? What if you could pile enough mass into a small enough region that light itself would be trapped? John Michell, an English natural philosopher and clergyman, proposed such an object. He imagined what he called a dark star, a body so massive and compact that its escape velocity would exceed the speed of light. Light, he reasoned, would rise briefly from its surface, slow, and then fall back, unseen by any distant observer. And that idea emerged not from wild speculation, but from Newtonian gravity and a simple understanding of light as particles. It was a quiet thought, almost fragile, and yet it contained the seed of something profound. What is striking is how easily this idea slipped into obscurity. Perhaps it was too unsettling. Or perhaps the universe, at that time, felt safer when its darkest corners remained theoretical. When the wave theory of light took hold, Michel's dark stars seemed less convincing. If light was a wave, not a particle, how could gravity capture it in the same way? And so the idea drifted, like a forgotten note in the margins of science. But it did not vanish. It waited. Then, in the early 20th century, our understanding of gravity itself changed completely. Einstein's general theory of relativity replaced the old idea of gravity as a force with something far stranger and more elegant. Mass and energy, he told us, curve space-time, and objects move along those curves. Gravity was no longer a pull, it was geometry. Space and time themselves could bend, stretch, and warp. And once you accept that, well, the possibility of extreme curvature becomes impossible to ignore. Soon after Einstein published his equations, solutions began to appear. Karl Schwarzschild, working under extraordinary circumstances during the First World War, found a solution that described space-time around a spherical mass. Hidden within his mathematics was a critical radius, a boundary beyond which space-time behaved in an unfamiliar way. Today, we call it the Schwarzschild radius. At the time, it looked like a mathematical curiosity, perhaps even a flaw. Few believed it described anything real. And Einstein himself, I suppose, was deeply skeptical. He suspected that nature would never allow matter to collapse into such an extreme state. This skepticism is important because it reminds us that science is not a straight path toward truth. It is shaped by intuition, bias, and the limits of imagination. The equations suggested that if enough mass were compressed into a small enough volume, space-time would pinch inward, forming a region from which nothing could return. But the idea seemed absurd. Stars, after all, were stable. They shone for millions or billions of years. The universe appeared calm, orderly. Why would it permit such catastrophic endings? And yet, quietly, the mathematics refused to let go. In the 1930s, as astrophysics matured, scientists began to understand how stars actually live and die. Nuclear fusion was discovered as the engine of stellar energy. Stars shine because they are balanced, gravity pulling inward, pressure from fusion pushing outward. But that balance is not eternal. When fuel runs out, gravity always wins. For small stars, the collapse halts, leaving behind white dwarfs. For larger ones, neutron stars. And then there came the unsettling realization that for stars beyond a certain mass, no known force could stop the collapse. Not electron pressure, not neutron pressure. Nothing. Still, many physicists resisted the conclusion. The idea that matter could collapse indefinitely, forming what we now call a singularity, felt like a breakdown of reason itself. Infinite density, infinite curvature. These were not just extreme conditions, they were signs that our theories had reached their limits. And that's the thing. Black holes did not enter science as triumphant discoveries. They arrived as embarrassments, as warnings that something was missing from our understanding. The very term black hole did not appear until the mid-20th century. Before that, these objects were described in cumbersome, uneasy language, gravitationally completely collapsed objects, frozen stars, singular solutions. It was John Wheeler who popularized the phrase black hole, and with it, a kind of conceptual clarity. A black hole was not a star, not a hole. It was a region of space-time defined by an event horizon, a boundary beyond which events could no longer influence the outside universe. The name stuck because it captured the essence of the idea in a way mathematics alone never could. Even so, acceptance was slow. For decades, black holes existed only on paper. There was no direct evidence, no observation that demanded their reality. They were solutions to equations, elegant and terrifying, but distant from experience. Many physicists treated them as useful fictions, tools to test general relativity rather than genuine cosmic inhabitants. And perhaps that caution was reasonable. After all, nature has surprised us before by choosing paths more subtle than our boldest predictions. But as telescopes improved, as radio astronomy opened new windows on the universe, strange things began to appear. Compact sources emitting enormous amounts of energy, stars orbiting invisible masses at impossible speeds, galactic centers behaving as though something extraordinarily heavy lurked within. Piece by piece, observation began to catch up with theory. The once abstract idea of a black hole started to acquire weight, influence, presence. What fascinates me most about this early history is how human it is. The idea of black holes did not emerge fully formed. It was shaped by doubt, by resistance, by the slow accumulation of insight. It reminds us that even the most radical truths often begin as whispers, easily ignored. And perhaps that is fitting, because black holes themselves do not announce their presence loudly. They reveal themselves indirectly through their effects on the world around them. At a deeper level, the history of black holes is also the history of our changing relationship with reality. Newton's universe was predictable, mechanical, and comforting. Einstein's universe was flexible, dynamic, and strange. Black holes push that strangeness to its limit. They force us to confront the possibility that space and time are not passive stages but active participants in the cosmic drama. They suggest that the universe can fold in on itself, hiding regions forever beyond our reach. And yet, there is something profoundly humbling here. Black holes were not invented by human imagination alone. They emerged when we listened carefully to nature, when we followed the mathematics even when it led us somewhere uncomfortable. They remind us that the universe does not owe us simplicity. It owes us only consistency. As we move forward, as theory and observation continue their quiet conversation, the question shifts. Not whether black holes exist, but how they come to be. What processes drive a star toward such an extreme fate? What decides whether collapse halts or continues? Because once you accept that black holes are real, truly real, the next natural step is to ask how the universe creates them, and what happens in those final moments when gravity overwhelms everything else, drawing us inevitably toward the story of stellar death and cosmic birth that awaits just ahead. And so, having accepted that black holes are not mere tricks of mathematics, but genuine outcomes allowed by the laws of nature, our curiosity naturally drifts toward a deeper and more unsettling question. How does the universe actually make one? What sequence of events could possibly compress matter so completely that space-time itself gives way? Well, to answer that, we must return to something far more familiar, something you can see with the naked eye on a clear night. A star. A star, you see, is not a static object. It is a long negotiation, a delicate truce between opposing forces. Gravity is always there, patient and relentless, pulling matter inward, trying to make the star smaller, denser, quieter. Pushing back against it is energy, released from nuclear fusion deep in the stellar core, where lighter elements are fused into heavier ones, releasing vast amounts of heat and pressure. For most of a star's life, these two influences are in balance. The star shines because it is not yet ready to give in. But that balance depends entirely on mass. And that's the thing. Mass is destiny in the life of a star. A small star, like our sun, lives gently and dies quietly. When its fuel runs out, it sheds its outer layers and leaves behind a dense but stable remnant, a white dwarf. Gravity pulls, but not strongly enough to cause further collapse. The universe, in that case, finds a compromise. For more massive stars, however, the story is very different. These giants burn hotter and faster, racing through their nuclear fuel in a fraction of the time. As fusion progresses, the core builds heavier and heavier elements until eventually it reaches iron. And iron, well, iron is a dead end. Fusing iron does not release energy. It consumes it. The engine that held gravity at bay sputters, then stops. At that moment, the star's core is suddenly unsupported. Gravity, which has been waiting all along, takes over completely. The core begins to collapse under its own weight, falling inward at a significant fraction of the speed of light. And this is where intuition often fails us. We tend to imagine a slow implosion, something dramatic but gradual. In reality, the collapse of a stellar core happens extraordinarily fast. In a matter of seconds, a region once larger than the Earth can be crushed down to the size of a city. For some stars, the collapse is halted. If the remaining core mass is below a certain threshold, neutron degeneracy pressure intervenes. Protons and electrons are forced together, forming neutrons, and the core becomes a neutron star, an object so dense that a teaspoon of its material would outweigh a mountain. The outer layers of the star rebound off this suddenly rigid core, producing a supernova explosion, one of the most violent events in the universe. But not all stars are saved by this last stand. There is a critical limit, a boundary written into the laws of physics. If the core is too massive, even neutron pressure is not enough. Gravity overwhelms every known force. There is no mechanism left to stop the collapse. And that is the birth of a stellar black hole. It is important to say this clearly. Not every dying star becomes a black hole. Only the most massive ones do. Mass determines whether collapse halts or continues. This is not a matter of chance or chaos, but of precise physical thresholds. Below them, matter finds stability. Above them, it does not. As the core collapses beyond this point, it shrinks inexorably. Density rises without limit. Space-time curves more and more sharply around it. Eventually, a boundary forms, the event horizon, enclosing the collapsing matter. From the outside, this boundary appears to freeze in time. The infalling material seems to slow, redshift, and fade, never quite crossing the horizon. But from its own perspective, the fall continues, uninterrupted, toward an unknown interior. And here is a subtle but crucial detail. There is no explosion inside a black hole. The dramatic supernova happens outside, driven by processes occurring before the event horizon fully forms. Inside the horizon, there is no outward force, no rebound, no release. Collapse is absolute. The word black hole sometimes suggests violence, a tearing or ripping of space, but the reality is quieter and far more unsettling. It is a silent surrender to gravity. Perhaps you have heard the phrase that black holes suck things in. That is not quite right. From a distance, a black hole behaves just like any other object of the same mass. If our sun were magically replaced by a black hole of equal mass, the planets would continue orbiting as they do now. Nothing would suddenly be dragged inward. The difference lies only in what happens very close to the object, where space-time curvature becomes extreme. The formation process itself is a kind of cosmic narrowing. Possibilities are stripped away one by one. First, nuclear fusion can no longer resist gravity. Then electron pressure fails. Then neutron pressure fails. Each stage represents a known chapter of physics closing its doors. What remains is a regime we do not fully understand. From the perspective of general relativity, collapse continues until matter reaches a singularity, a region of infinite density and curvature. But many physicists suspect that this description is incomplete. Infinity, after all, often signals that a theory has been pushed beyond its limits. Quantum effects, which we do not yet fully know how to incorporate into gravity, may alter the final outcome. But whatever the ultimate truth, the path to black hole formation is clear. It is driven by mass, by exhaustion, by the simple fact that gravity does not tire. And, I think there is something deeply poetic in that. Stars spend their lives resisting collapse, shining against gravity's pull. Black holes are what happens when resistance finally becomes impossible. They are not failures of stars, but the natural conclusion of a life lived too intensely. The timescales involved are also worth reflecting on. A massive star may burn for millions of years, yet its final collapse happens in seconds. A lifetime of balance ends in a moment of inevitability. The universe, it seems, is quite comfortable with such a symmetry. Long preparation, sudden transformation. Once formed, a stellar black hole is remarkably simple. According to theory, it can be described entirely by just a few properties: its mass, its spin, and its electric charge. All the complexity of the original star, its composition, its structure, its history, disappears behind the event horizon. This idea, sometimes called no hair, is both elegant and disturbing. It suggests that black holes erase information about their origins, at least from the outside world. Yet even as black holes form through collapse, they do not exist in isolation. They are born into environments shaped by the very explosion that heralded their creation. Surrounding gas, dust, and stellar debris may swirl around them, forming accretion disks and emitting intense radiation. In this way, the death of a star can give rise to some of the brightest phenomena in the universe. And that brings us to an interesting realization. Black holes are not merely endpoints. They are active participants in cosmic evolution. The collapse that forms them redistributes matter and energy, seeds future generations of stars, and reshapes its surroundings. Destruction and creation are woven together, inseparable. As our understanding of stellar collapse deepened, it also became clear that stellar black holes are just one part of a much broader family. The same principles of gravity and mass that govern their birth can operate on vastly different scales. If stars can collapse into black holes, what about clusters of stars or entire galactic cores? What happens when collapse is driven not by a single dying sun, but by the slow accumulation of matter over cosmic time? And so, as we follow this thread, from stellar death to gravitational inevitability, our gaze naturally lifts outward, beyond individual stars, beyond supernovae and remnants, toward a universe populated by black holes of many kinds, with masses ranging from a few times that of our sun to millions or billions of suns gathered at the hearts of galaxies. To understand those, we must now widen our perspective and explore the different varieties of black holes that the universe appears to have created, each one a variation on the same profound theme written into gravity itself. And as we widen our gaze beyond the final moments of a single collapsing star, something rather remarkable begins to emerge. The universe, it seems, does not settle for just one kind of black hole. Instead, it produces a whole family of them, varied in mass, influence, and mystery, each shaped by a different path through cosmic history. And this is where the story becomes richer, because once you stop thinking of black holes as rare oddities and start seeing them as a population, you realize they are woven deeply into the structure of the universe itself. The most familiar members of this family are stellar black holes, the natural descendants of massive stars we have just been talking about. These are the black holes born in violence, forged in the collapse of stellar cores and announced to the cosmos by supernova explosions. Their masses typically range from a few times that of our sun to perhaps several tens of solar masses. On cosmic scales, they are modest, and yet, even these comparatively small black holes represent an astonishing concentration of matter. Imagine compressing several suns into a region no larger than a city, and you begin to sense just how extreme they are. Stellar black holes are thought to be common. Our galaxy alone may contain millions of them, quietly drifting through space, invisible unless they interact with their surroundings. Most are dark, isolated, betraying their presence only through subtle gravitational effects. Others are more dramatic, locked in binary systems with companion stars. In these pairings, matter can be stripped from the companion and spiral inward, heating up and glowing fiercely before crossing the point of no return. It is often through these luminous displays that stellar black holes first revealed themselves to us. But even as astronomers were becoming comfortable with the idea of stellar black holes, evidence began to surface for something far larger and far stranger. At the centers of galaxies, including our own Milky Way, stars were observed orbiting an unseen mass at extraordinary speeds. The only plausible explanation was an object millions of times more massive than the Sun, confined to a remarkably small volume. These were not the remnants of single stars. They were something else entirely. Supermassive black holes. Supermassive black holes occupy a different realm altogether. With masses ranging from millions to billions of solar masses, they dominate the gravitational landscape of their host galaxies. And yet, curiously, they do not dominate in the way we might instinctively fear. They do not roam the galaxy devouring stars at random. Instead, they sit at the center, largely quiescent, influencing their surroundings through gravity and, at times, through immense releases of energy. What is perhaps most astonishing is how common these giants appear to be. Nearly every large galaxy we observe seems to host a supermassive black hole at its core. This suggests a deep connection between the formation of galaxies and the formation of these enormous objects. The growth of a galaxy and the growth of its central black hole appear to be intertwined, as if they are two expressions of the same underlying process. And that raises a profound question. How do such enormous black holes form? The collapse of a single star, no matter how massive, cannot produce something millions of times the mass of the Sun. So where do these giants come from? There are several ideas, none yet fully confirmed. Perhaps they grew from smaller seed black holes, remnants of the first generation of stars, gradually feeding on gas and merging with one another over cosmic time. Or perhaps, under the right conditions, vast clouds of gas collapse directly into massive black holes, bypassing the stellar phase altogether. Between the familiar stellar black holes and the colossal supermassive ones lies a more elusive category, intermediate mass black holes. These objects, with masses ranging from hundreds to hundreds of thousands of solar masses, have long been something of a missing link. For years, their existence was debated. They were too massive to be explained by normal stellar collapse, yet too small to comfortably fit into models of galactic centers. Gradually, hints began to appear. Dense star clusters showed signs of harboring unseen massive objects. Certain ultraluminous X-ray sources seemed too bright to be powered by stellar black holes alone. These clues suggest that intermediate mass black holes may indeed exist, perhaps formed through repeated mergers of stellar black holes in crowded environments, or through the collapse of unusually massive primordial stars. If confirmed in large numbers, intermediate mass black holes could help explain how supermassive black holes grew so quickly in the early universe. They might represent stepping stones, a ladder of mass built through gravity's relentless ability to draw matter together. And that idea fits beautifully with a broader theme in cosmology, that complex structures often arise not in one leap, but through a sequence of incremental steps. Then there is perhaps the most speculative member of the family, primordial black holes. These hypothetical objects are unlike any of the others because they would not be born from stars or galaxies at all. Instead, they may have formed in the earliest moments after the Big Bang, when the universe was hot, dense, and turbulent. Tiny fluctuations in density, amplified by extreme conditions, could have collapsed directly into black holes. Primordial black holes could span an enormous range of masses, from far smaller than a mountain to many times the mass of the Sun. Some might have evaporated long ago through quantum processes, while others could still exist today, drifting through space, invisible and enigmatic. There has even been speculation that such black holes could account for some or all of the dark matter in the universe, though this remains an open and hotly debated question. What unites all these varieties is gravity, operating across vastly different scales, yet following the same fundamental rules. Whether formed from the death of a star, the slow growth at a galactic center, or the violent fluctuations of the early cosmos, black holes are expressions of gravity taken to its extreme conclusion. They differ in mass and origin, but not in essence. It is also worth reflecting on how we know about these different types. We do not see black holes directly. We infer their existence through motion, through light emitted by surrounding matter, through the ripples they send through space-time itself. In recent years, gravitational wave detectors have allowed us to listen to the mergers of black holes, revealing populations of stellar black holes with masses larger than many had expected. These observations hint that our census of black holes is still incomplete. As we catalog these objects, patterns begin to emerge. Stellar black holes trace the life cycles of massive stars. Supermassive black holes trace the formation and evolution of galaxies. Intermediate mass black holes may trace the dynamics of dense stellar systems. Each category tells a different chapter of the same story, a story about how matter organizes itself under gravity. And perhaps the most humbling realization is that black holes are not rare exceptions. They are common outcomes. Given enough mass and time, gravity tends toward collapse. The universe seems quite comfortable producing black holes wherever conditions allow. They are not anomalies. They are part of the natural order. This diversity also forces us to confront our assumptions. For a long time, black holes were imagined as isolated monsters lurking in the dark. Now we see them as central players in cosmic ecosystems. They influence star formation, shape galaxies, and may even hold clues to the earliest moments of the universe. As our understanding of the different kinds of black holes deepens, attention naturally shifts from what they are to how they behave. What does space-time look like near one of these objects? How does gravity act when curvature becomes extreme? What happens at the boundary, where escape becomes impossible? To explore those questions, we must now move closer, leaving behind questions of mass and origin, and approaching the structure that defines all black holes, the strange geometry that surrounds them and separates the known universe from whatever lies beyond. And so, as our attention shifts from the many kinds of black holes scattered throughout the cosmos, our curiosity naturally pulls us closer, inward, toward the boundary that defines them all. No matter their mass or origin, every black hole presents the universe with the same quiet question. Where exactly does the point of no return begin? What does the space around a black hole actually look like? And, this is where language begins to struggle, because the external structure of a black hole is not a thing you can touch or see. It is a geometry, a shape carved into space-time itself. At the heart of this structure lies the event horizon. It is often described as a surface, but that description can be misleading. The event horizon is not made of matter. It has no thickness, no texture, no physical substance. It is simply a boundary in space-time, a line drawn not in space alone, but in time as well. Cross it, and all possible futures point inward. Escape is no longer an option, not because something blocks the way, but because the way out has ceased to exist. From far away, the event horizon appears almost passive. There is no warning sign, no glowing edge. A black hole does not announce itself with light or sound. And that's the thing. The most dramatic boundary in the universe is also the quietest. If you were drifting freely through space and crossed the event horizon of a sufficiently large black hole, you might not notice anything special at that exact moment. Locally, the laws of physics still feel familiar. Your body would not be crushed instantly. Your clock would tick as usual. It is only when you consider the global picture, the structure of space-time as a whole, that the finality of that crossing becomes clear. The size of this boundary is determined by what we call the Schwarzschild radius, a length that depends entirely on mass. Double the mass of a black hole, and its Schwarzschild radius doubles as well. For a black hole with the mass of the Sun, this radius is only a few kilometers. For a supermassive black hole with millions of solar masses, it can be larger than the orbit of Mercury. And that leads to an important insight. Bigger black holes are, in a sense, gentler at their horizons. The tidal forces that stretch and squeeze objects grow weaker as the black hole grows larger, at least at the boundary itself. This brings us to one of the most persistent misconceptions. Black holes do not have solid surfaces. There is no hard shell you could land on, no cosmic floor waiting at the edge. The event horizon is not a place where matter piles up. Matter passes through it, never to be seen again, at least not by the outside universe. The black hole does not fill up like a container. Its mass increases, and with it, the size of the horizon, but nothing accumulates at the boundary. Another common image is that of a central suction point, a kind of cosmic drain pulling everything inward. But gravity does not work that way. A black hole does not reach out and grab distant objects any more than the sun does. From afar, its gravitational influence is indistinguishable from that of any other object with the same mass. Orbits remain stable. Stars circle calmly. The drama unfolds only when something ventures very close. As you approach a black hole, space-time itself begins to curve more noticeably. Paths that once felt straight begin to bend. Light rays arc inward. Time slows relative to distant observers. This gradual distortion is key. There is no sudden transition, no sharp cliff at the horizon when viewed locally. Instead, The universe gently but inexorably guides everything inward, like a river accelerating toward a waterfall. And that metaphor is more than poetic. Some physicists describe the region around a black hole as a flow of space itself. Far away, space is calm. Closer in, it begins to move inward, slowly at first, then faster. At the event horizon, the inward flow reaches the speed of light. Inside, it exceeds it. No matter how fast you try to swim outward, the current is stronger. Escape becomes impossible not because you are weak, but because space-time itself is moving. From the perspective of a distant observer, something strange happens. An object falling toward a black hole appears to slow down as it approaches the horizon. Its light becomes increasingly redshifted, stretched to longer wavelengths, fading into darkness. In this view, the object never quite crosses the horizon. It freezes, suspended in time. But this is an illusion created by perspective. For the falling object, the crossing happens in finite time. Reality, it seems, depends on where you stand. This difference in perspective is one of the most profound lessons black holes teach us. There is no single, absolute account of events that all observers must agree upon. Space and time are woven together, and different paths through space-time reveal different truths. Both viewpoints are valid within their own frames of reference, and that can feel deeply unsettling because it challenges our instinctive belief in a shared, universal now. The space outside a black hole is also shaped by rotation. Many black holes spin, inheriting angular momentum from the matter that formed them. Around a rotating black hole, space-time itself is dragged along, twisted into a slow whirlpool. This effect, called frame dragging, means that nothing can remain perfectly still near the black hole. There exists a region outside the event horizon where space-time is forced to rotate, known as the ergosphere. Within it, objects can still escape, but only if they move in the direction of the spin. Again, there is no surface here, no material boundary. These regions are defined purely by geometry. They are properties of space-time itself, responding to mass and motion. And that's the thing. Black holes are not objects sitting in space. They are modifications of space. They are solutions to the equations that tell space-time how to curve. Perhaps the most counterintuitive aspect of a black hole's exterior is how ordinary it can seem. Stand far enough away, and nothing looks unusual. Stars orbit as expected. Light travels in predictable paths. It is only when we probe the region close to the horizon that the true strangeness reveals itself. The universe, it seems, hides its most extreme behaviors behind a veil of normality. This has profound implications for observation. Because we cannot see past the event horizon, everything we know about black holes comes from their influence on their surroundings. The external structure is all we have access to, and remarkably, that structure is simple. In theory, a black hole's exterior can be fully described by just a few parameters: mass, spin, and charge. All other details are erased from view. This simplicity is deceptive. It suggests a kind of cosmic censorship, a rule that keeps the most violent and incomprehensible regions of space-time hidden from the rest of the universe. The event horizon acts as a curtain, separating what can be known from what cannot. And that raises questions that are as philosophical as they are physical. What does it mean for something to exist if it can never influence the outside world again? As we trace the gentle but relentless curvature of space toward the horizon, it becomes clear that the exterior of a black hole is not just a prelude to destruction. It is a carefully structured region governed by precise laws. It teaches us how gravity reshapes reality, how time and space lose their independence, how perspective becomes everything. And yet, for all this elegance, the exterior structure is only the beginning. The horizon marks the limit of our observational reach, not the end of the story. Beyond it lies a realm where our current theories falter, where density and curvature may become infinite, where familiar concepts dissolve entirely. To understand what a black hole truly is, we must eventually confront what lies inside, the mysterious interior where space-time itself seems to tear, and where the word singularity enters our language, heavy with uncertainty and wonder. And once that silent boundary has been crossed, once the universe outside can no longer be reached, our language grows hesitant. Our metaphors thin, and our confidence begins to fade, because inside a black hole we are no longer guided by observation. There is no telescope, no signal, no message that can return to us. Everything we say from this point onward is inferred, extrapolated, whispered by mathematics rather than confirmed by light. And that makes this region not only the most extreme place in the universe, but also the most honest mirror of our ignorance. According to general relativity, the inward journey does not end at the event horizon. Space continues to curve more and more violently, funneling all possible paths toward a central fate. This destination is called the singularity, a word that carries a certain finality to it. In the equations, it appears as a point where density becomes infinite, where space-time curvature diverges without bound, and where the known laws of physics cease to function in any meaningful way. But it is important to pause here. A singularity is not an object in the usual sense. It is not a thing floating inside the black hole. It is not even properly a place within space. Rather, it is a breakdown of description. It marks the point where our mathematical tools fail to give sensible answers. In that sense, a singularity tells us less about the universe and more about the limits of our theories. From the perspective of classical general relativity, once inside the horizon, the singularity is unavoidable. It lies not in your future as a destination you might reach, but as a moment in time. Inside a black hole, the roles of space and time exchange. Moving inward is no longer a choice, just as moving forward in time is not a choice outside the black hole. The singularity becomes as inevitable as tomorrow. This inversion is one of the strangest consequences of black hole physics. Outside, you can choose where to go in space, but not whether to move into the future. Inside, you may have some freedom of direction, but the singularity lies ahead in time, unavoidable. And that challenges our most basic intuitions about motion and causality. It suggests that the structure of space-time itself can change character depending on where you are. As matter approaches the singularity, tidal forces grow without limit. Differences in gravitational pull between different parts of an object become enormous. In popular descriptions, this leads to the idea of spaghettification, where objects are stretched lengthwise and compressed sideways. While the details depend on the mass of the black hole, the underlying principle remains. Gravity does not act uniformly. It tears. And yet, for large black holes, this tearing does not begin at the horizon. You could cross that boundary intact, unaware of your fate. It is only deeper inside that the violence becomes overwhelming. This separation between horizon and singularity reinforces an unsettling idea. The event horizon is not dangerous because of local forces. It is dangerous because of what it makes inevitable. What actually exists at the singularity remains unknown. Infinite density is a mathematical artifact, not something we believe nature truly permits. In other areas of physics, infinities signal incompleteness. When classical electromagnetism produced infinite energies, quantum mechanics resolved the problem. When calculations predicted ultraviolet catastrophes, new theories emerged. Many physicists believe the same must be true here. Quantum theory, which governs the behavior of matter and energy at the smallest scales, has not yet been successfully unified with general relativity. Near the singularity, both theories are essential. Gravity is immense, and quantum effects cannot be ignored. Our current equations cannot handle this regime. They speak past one another, and so the singularity sits at the crossroads of modern physics, a signpost pointing toward a deeper theory we have yet to discover. Some hypotheses suggest that singularities may not exist at all. Instead, quantum effects might smear out the collapse, replacing the singularity with something finite but exotic, a region of extreme but bounded density. Others propose that space-time may continue beyond the classical singularity into another region, perhaps another universe entirely. These ideas remain speculative, but they reflect a growing discomfort with the idea of true infinities in nature. There is also the question of information. As matter falls into a black hole, all details of its structure appear to vanish from the outside universe. Mass, charge, and spin remain, but everything else is lost. If the singularity truly destroys information, this would violate a fundamental principle of quantum mechanics, that information is conserved. This tension has become one of the deepest puzzles in theoretical physics. But notice something subtle. The singularity itself may not be the culprit. The paradox arises because information crosses the event horizon and becomes inaccessible, not necessarily because it is destroyed at the center. The singularity, hidden behind the horizon, may be less important than the boundary that conceals it. And this shifts our attention away from the center and back toward the structure of space-time itself. Another unsettling feature of singularities is that they are not points in space in the way we normally imagine. In rotating black holes, for example, the singularity takes the form of a ring. In more general solutions, it can be extended, distorted, or even time-dependent. This reinforces the idea that singularities are not objects but features of space-time geometry. And yet, despite all this uncertainty, singularities play a crucial role in our understanding. They tell us that gravity, when unchecked, leads to extremes beyond our current comprehension. They mark the boundary between known physics and whatever lies beyond. They force humility upon us. They remind us that the universe is under no obligation to conform to our expectations. It is also worth reflecting on how strange it is that such a region can exist at all. A place where time ends, a future that cannot be extended. Outside a black hole, the universe feels open-ended. There is always a next moment. Inside, the singularity represents a terminus, a limit not just of space, but of temporal extension. And that has philosophical weight. It invites us to reconsider what we mean by existence and duration. Yet even here, caution is needed. We often imagine falling into a black hole as a dramatic plunge toward destruction. But from the perspective of the infalling observer, much of the journey may feel ordinary, even calm. The true drama unfolds in regions we cannot describe, governed by laws we do not yet possess. The singularity, if it exists, is not an explosion or an event. It is a condition. In this sense, the interior of a black hole is not merely a place of endings. It is a laboratory for the future of physics. It is where our theories are tested to breaking point, where assumptions fail, where new principles may eventually emerge. And that's the thing. Black holes are not just astrophysical objects. They are conceptual tools, pushing us toward deeper questions about reality itself. As we confront the unknowability of the singularity, another realization begins to take shape. Much of what makes black holes strange is not confined to their interiors. The effects of extreme gravity spill outward, shaping the behavior of time and space well beyond the horizon. Even without crossing that boundary, observers can experience phenomena that challenge intuition. Time slows, paths bend, simultaneity dissolves. And so, having followed matter inward to the limits of description, our attention naturally shifts again, outward, but not far, toward the region just outside the horizon, where gravity is intense but physics still speaks clearly. Toward the strange relationship between time and space near a black hole, where clocks tick at different rates and distances lose their meaning, and where the everyday experience of time begins to unravel under the quiet, relentless influence of curvature itself. And so, having brushed up against the unknowable interior, having followed matter and meaning toward the singularity where our equations fall silent, we find ourselves drawn back outward, not away from the black hole, but closer to its edge. Because some of the strangest and most revealing effects of a black hole do not require crossing the horizon at all. They unfold just outside it, in the region where gravity is fierce but still speaks a language we can understand. And here, time itself begins to behave in ways that feel deeply unsettling, even intimate, because time is something we all think we know. Far from a black hole, time feels universal. Seconds tick by with reassuring regularity. Your clock agrees with mine. Cause precedes effect. But near a black hole, that shared rhythm fractures. Time slows down, not as an illusion, not as a trick of perception, but as a physical effect, written into the geometry of space-time. The closer you are to a massive object, the more slowly your clock ticks compared to one far away. This is gravitational time dilation, and near a black hole, it becomes extreme. Imagine a clock hovering just above the event horizon. To an observer watching from far away, that clock appears to tick more and more slowly as it approaches the boundary. Each second stretches longer than the last. Light emitted from the clock is redshifted, losing energy as it climbs out of the gravitational well. Eventually, the clock seems to freeze, its final tick drawn out endlessly, fading into darkness. From this distant perspective, time near the horizon nearly comes to a halt, and yet, from the perspective of the clock itself, nothing unusual happens. It ticks normally. Time feels ordinary. This is not a contradiction. It is a consequence of relativity. Time is not absolute. It depends on where you are and how you move through space-time. Both perspectives are correct within their own frames. And that realization alone is enough to shake our confidence in the idea of a single, objective present. This effect is not speculative. We have measured time dilation near Earth using atomic clocks. Clocks on satellites tick slightly faster than those on the ground. GPS systems must account for this difference to function properly. Near a black hole, the same principle applies, but amplified to an almost unimaginable degree. Gravity does not just bend space, it stretches time. Now consider someone falling toward a black hole. To a distant observer, their descent appears to slow, never quite completing. But for the falling observer, time continues forward, and the horizon is crossed in a finite interval. Their experience of time diverges completely from that of the watcher left behind. This divergence is not merely philosophical, it is built into the structure of reality. Space, too, undergoes a transformation. Near a black hole, distances lose their familiar meaning. Radial distances stretch. Circumferences behave strangely. Paths that once seemed straight begin to curve inward. The geometry of space becomes non-Euclidean, reshaped by mass and energy. What we call gravity is not a force acting within space, but the manifestation of this curvature. One useful way to picture this is the idea of space-time as a flowing medium. Far from the black hole, space is nearly still. As you move closer, it begins to flow inward, slowly at first, then faster. Near the horizon, the inward flow reaches the speed of light. Inside, it exceeds it. This is why escape becomes impossible. You are not being pulled back by a force. You are being carried by space-time itself. This flowing space analogy also helps explain why there is no absolute frame of reference near a black hole. There is no privileged observer who can claim to see events as they truly are. All descriptions depend on motion and position. Simultaneity becomes relative. Events that appear simultaneous to one observer may not be so to another. Time, it turns out, is not a universal backdrop, but an active participant. For someone falling toward a black hole, their experience of space is equally strange. Objects ahead appear distorted. Light from the outside universe is aberrated and blue-shifted, compressed into a shrinking patch of sky. The future of the external universe may even appear to unfold rapidly before their eyes, depending on the black hole's properties. The outside world seems to race ahead, while the infalling observer's own time feels normal. And that inversion is profoundly disorienting. At the same time, tidal effects begin to assert themselves. Differences in gravitational pull across the body stretch and squeeze. For stellar mass black holes, these effects become lethal well before the horizon. For supermassive black holes, they may remain mild until deep inside. This again reminds us that black holes are not all the same. Their impact on time and space depends on scale. What remains constant is the absence of any absolute reference frame. There is no cosmic clock ticking uniformly for everyone. Near a black hole, this becomes impossible to ignore. Each observer carries their own time, shaped by gravity and motion. And that's the thing. Black holes do not just distort space-time. They expose its true nature. We often speak of space-time as if it were a thing, but near a black hole, it behaves more like a relationship. Time and space are not separate entities. They are aspects of a single structure. Change one, and the other responds. Near the horizon, time slows relative to faraway observers, while space stretches inward. The two effects are inseparable. This has deep consequences for causality. The order of events can depend on perspective. Signals sent outward from near the horizon take longer and longer to reach distant observers. Eventually, communication becomes effectively impossible. The horizon marks not just a spatial boundary, but a causal one. Beyond it, events cannot influence the outside universe. And yet, even without crossing that boundary, the presence of extreme time dilation has observable consequences. Matter orbiting close to a black hole emits radiation that carries the imprint of relativistic effects. Spectral lines are shifted. Light curves are distorted. These signatures allow us to test general relativity in regimes far beyond anything we can create on Earth. In this way, black holes become laboratories for the nature of time itself. Perhaps the most unsettling realization is that there is no single answer to the question, what is happening now near a black hole? Now depends on where you are. The universe does not provide a universal present. It provides local experiences, stitched together by geometry. And that challenges something deeply human. Our desire for a shared moment, a common flow of time binding us all. Yet there is also beauty here. Time slowing near a black hole is not arbitrary. It is lawful, predictable, elegant. It follows directly from the same equations that describe planetary orbits and gravitational waves. The universe does not break its rules near black holes. It reveals them more clearly. As space bends and time stretches, another effect becomes unavoidable. Energy is released. Matter falling into the deep gravitational well heats up. Motion becomes violent. Friction and compression turn gravity into light. And so, having traced how black holes reshape time and space, our attention is drawn to a seeming contradiction. How can something defined by darkness become one of the brightest phenomena in the universe? To answer that, we must turn to the luminous environments surrounding black holes, where gravity, motion, and radiation combine to create some of the most energetic displays nature has to offer. And so we arrive at what feels like a contradiction, one that has puzzled and delighted astronomers for decades. How can the darkest objects in the universe become some of the brightest? How can regions defined by the impossibility of escape be associated with torrents of light that outshine entire galaxies? Well, you see, the answer lies not in the black hole itself, but in its surroundings. Black holes do not shine, but the universe around them most certainly does. As matter begins its slow, inevitable descent toward a black hole, it rarely falls straight in. The cosmos is rarely that tidy. Gas and dust carry angular momentum, and so, instead of plunging directly inward, they spread out into a flattened, rotating structure known as an accretion disk. This disk is where the real drama unfolds. Friction between neighboring layers, magnetic turbulence, and relentless gravitational shear heat the material to extraordinary temperatures. The closer the matter spirals inward, the faster it moves, and the hotter it becomes. By the time gas reaches the inner regions of the disk, it can be heated to millions of degrees. At these temperatures, atoms are stripped apart. Electrons are torn from nuclei. The disk becomes a seething plasma, glowing intensely across the electromagnetic spectrum. And this is one of the great ironies of black hole physics. The light we associate with them is produced not by the hole itself, but by matter desperately trying not to fall in. In fact, accretion onto black holes is one of the most efficient energy-generating processes known. As matter spirals inward, a significant fraction of its mass is converted into energy far more efficiently than nuclear fusion in stars. A black hole feeding actively can release enormous amounts of radiation, especially in X-rays. These X-rays are among the brightest sources in the sky, detectable across vast cosmic distances. This is why black holes were first discovered not through darkness, but through light. Astronomers noticed compact, flickering X-ray sources that could not be explained by ordinary stars. They saw gas heated beyond stellar limits, emitting energies that demanded a deep gravitational well. Slowly, the pieces came together. Something invisible was powering these cosmic beacons. The light from an accretion disk carries the fingerprints of extreme physics. Relativistic effects distort spectral lines. Time dilation alters variability. The inner edge of the disk marks the last stable orbit, a boundary set by spacetime itself. Beyond that point, matter plunges inward too quickly to radiate efficiently. The disk does not extend all the way to the horizon. There is a gap where gravity wins decisively. And then there are the jets. In some systems, black holes produce narrow, powerful beams of particles that shoot outward along their rotation axes at nearly the speed of light. These jets can extend for thousands or even millions of light years, piercing the surrounding galaxy and beyond. Their exact origin remains an active area of research, but magnetic fields twisted by the rotating disk and the spinning black hole itself appear to play a crucial role. These jets are astonishing in scale and influence. They carry enormous amounts of energy far from the black hole, heating interstellar gas, regulating star formation, and reshaping entire galaxies. Once again, the black hole is not a passive sink. Through its interaction with surrounding matter, it becomes an engine, converting gravitational potential into motion, heat, and light. It is important to emphasize that the black hole itself remains dark. No light escapes from within the event horizon. All the radiation we observe originates outside, in the disk and jets. The black hole is revealed by its impact, not its appearance. And that is a recurring theme in this story. Black holes teach us to look for influence rather than substance. Different black holes shine in different ways. Stellar mass black holes in binary systems produce X-ray outbursts as they feed intermittently from companion stars. Supermassive black holes at galactic centers can enter active phases, becoming quasars or active galactic nuclei, outshining the combined light of billions of stars. In quieter times, they may be almost invisible, sipping rather than feasting. The variability of this emission is itself a clue. Light from accretion disks flickers and flares on timescales linked to the size of the emitting region. Rapid changes imply compact sources. By studying these variations, astronomers can infer the presence of a black hole even when it cannot be resolved directly. Time becomes a diagnostic tool. And there is something deeply poetic here. The same object that traps light forever can be surrounded by matter that radiates so intensely that it becomes visible across the universe. Darkness framed by brilliance. Silence bordered by noise. The black hole remains mute, but its environment tells a loud and intricate story. These luminous processes also reveal how black holes interact with their surroundings on the largest scales. Jets can suppress or trigger star formation. Radiation from active nuclei can heat galactic gas, preventing it from cooling and collapsing into new stars. In this way, black holes exert a form of feedback, influencing the growth and evolution of their host galaxies. This connection becomes especially clear when we look at supermassive black holes. Their masses correlate with properties of the galaxies they inhabit. It is as if the black hole and the galaxy grow together, each shaping the other's fate. The light emitted during active phases is not merely a byproduct. It is a mechanism of regulation. And that challenges the old image of black holes as simple destroyers. They are not cosmic vacuum cleaners indiscriminately swallowing everything. They are participants in a delicate balance, sometimes violent, sometimes subtle, but always consequential. Their light, indirect though it may be, becomes a means of cosmic communication. As we study these luminous environments, we also gain new tests of fundamental physics. The motion of matter near the horizon probes strong gravity. The polarization of emitted light encodes information about magnetic fields and space-time geometry. Each photon carries a message from a region where gravity and motion are pushed to their limits. Yet even as black holes shine through their surroundings, the question of scale looms ever larger. Stellar black holes influence their immediate neighborhoods. Supermassive black holes influence entire galaxies. The same processes, scaled up, produce profoundly different consequences. To understand this fully, we must zoom out once more, from disks and jets to galaxies themselves. Because the most dramatic role black holes play is not in individual systems, but in shaping the large-scale structure of the universe. Their light and energy reach far beyond their immediate vicinity, affecting star formation, gas dynamics, and galactic architecture. And so, having seen how black holes can blaze without shining themselves, we are ready to explore their partnership with galaxies to understand how these enigmatic objects help guide the growth and evolution of the vast stellar cities they inhabit. And as we step back from the fierce brilliance of accretion disks and the vast reach of relativistic jets, a quieter but far more consequential picture begins to take shape. Black holes, especially the supermassive ones, are not merely dramatic actors flaring briefly in cosmic history. They are long-term partners of galaxies themselves. Almost every large galaxy we observe appears to host a supermassive black hole at its center, and that simple fact carries profound implications. It suggests that galaxies and black holes did not grow independently, but together, locked in a slow, intricate dance that has shaped the universe we see today. At first glance, this seems counterintuitive. A galaxy contains hundreds of billions of stars, vast clouds of gas, dark matter halos extending far beyond what we can see. A black hole, even a supermassive one, occupies a region smaller than our solar system. How could such a compact object matter on galactic scales? And this is where gravity and feedback quietly reveal their power. Observations show a remarkable correlation between the mass of a galaxy's central black hole and properties of the galaxy itself, such as the mass of its central bulge or the velocity of stars orbiting near the core. This is not a coincidence. It is as if the galaxy somehow knows how massive its black hole should be, and the black hole knows how large the galaxy can grow. The relationship is too tight to be accidental. It points to a shared evolutionary history. In the early universe, galaxies were far more chaotic than they are today. Gas was abundant, mergers were common, star formation was intense. In these turbulent environments, supermassive black holes likely grew rapidly, feeding on the same gas that formed stars. When enough matter fell inward, the black hole would enter an active phase, blazing as a quasar and releasing enormous amounts of energy. This energy did not remain confined to the immediate vicinity of the black hole. Radiation and jets pushed outward, heating surrounding gas and driving powerful winds. These outflows could sweep gas out of the central regions of the galaxy, depriving it of the raw material needed to form new stars. In this way, the black hole acted as a regulator. When growth became too vigorous, it applied the brakes. And that's the thing. Supermassive black holes do not simply consume, they modulate. They prevent runaway star formation, shaping the size, structure, and fate of galaxies. Without this feedback, many galaxies would likely look very different, perhaps too massive, too bright, too short-lived in their star-forming phases. Crucially, this regulation does not require the black hole to be constantly active. Most of the time, supermassive black holes are quiet. They accrete matter slowly, emitting little radiation. But during brief, intense episodes, their influence can be transformative. A short quasar phase can alter the trajectory of a galaxy for billions of years. It is also important to dispel a persistent myth. Supermassive black holes do not sit at galactic centers devouring everything around them. The scales involved simply do not allow that. Stars orbit the central black hole much as planets orbit a star, stable and enduring. The black hole's gravitational influence dominates only very close to the center. Its larger impact comes not from direct consumption, but from energy released during accretion. In some galaxies, this energy takes the form of collimated jets that punch through interstellar gas, carving cavities and heating vast regions of the galactic halo. In galaxy clusters, jets from central black holes can prevent hot gas from cooling and collapsing, suppressing star formation across enormous volumes. Once again, the black hole acts less like a predator and more like a thermostat. There is also growing evidence that the growth of galaxies and black holes proceeds in parallel. When galaxies merge, their central black holes may eventually merge as well, releasing gravitational waves that ripple through space-time. These mergers contribute to the growth of supermassive black holes and help establish the observed correlations between black hole mass and galactic properties. At the same time, the inflow of gas during mergers can trigger both starbursts and black hole feeding. For a while, both grow rapidly. Then feedback intervenes. Gas is heated or expelled. Star formation slows. The galaxy settles into a quieter phase. This cycle, repeated across cosmic history, appears to be a fundamental pattern. And what I find particularly humbling is that this relationship seems almost inevitable. Given gravity, gas, and time, black holes and galaxies naturally influence one another. There is no need for fine-tuning. The laws of physics themselves encourage this coevolution. Even our own Milky Way bears the imprint of this partnership. At its center lies a supermassive black hole with a mass of about 4 million suns. It is currently quiet, barely accreting, but evidence suggests it was more active in the past. Echoes of past outbursts are imprinted in the surrounding gas, faint reminders that our galaxy too has experienced periods of black hole-driven change. On larger scales, the presence of supermassive black holes may help explain why galaxies fall into distinct categories, such as spirals rich in gas and star formation, and ellipticals dominated by old stars. Black hole feedback may play a role in shutting down star formation, nudging galaxies from one category to another. This realization reshapes our view of cosmic history. Galaxies are not just collections of stars evolving in isolation. They are dynamic systems, influenced by processes occurring at their very centers. The smallest scales can shape the largest outcomes, and yet despite this central role, supermassive black holes remain elusive. We infer their presence through stellar motions, gas dynamics, and energetic outbursts, but we rarely see them directly. They are felt more than seen, architects whose designs emerge over billions of years. As we reflect on this partnership between black holes and galaxies, another question quietly arises. If black holes can shape galaxies over cosmic time, what ultimately becomes of the black holes themselves? Do they last forever, eternal anchors at galactic cores? Or do they too have lifetimes, slow and subtle endings written not in gravity alone, but in quantum effects that whisper of impermanence even in the darkest places? To explore that possibility, we must turn from the grand scales of galactic evolution to the smallest scales of quantum physics, where an unexpected idea suggests that black holes may not be entirely black after all, and that even these seemingly eternal objects may slowly fade, particle by particle, into the fabric of the universe. And so, having seen how black holes can shape galaxies over billions of years, how they can regulate the birth of stars, and quietly guide the architecture of the cosmos, a new and rather unsettling thought begins to surface. We tend to think of black holes as eternal. Once formed, they feel like the ultimate endpoints, perfect prisons from which nothing ever escapes. But in the early 1970s, a remarkable idea emerged that challenged this assumption at its core. An idea that suggested black holes are not completely black, and not completely immortal either. Stephen Hawking, working at the intersection of general relativity and quantum mechanics, asked a deceptively simple question. What happens to quantum fields near the event horizon? In everyday space, quantum theory tells us that empty space is never truly empty. It seethes with fluctuations. Pairs of particles and antiparticles constantly pop into existence and annihilate one another almost instantly. Normally, this restless activity leaves no lasting trace. But near a black hole, the presence of the event horizon changes the rules. According to Hawking's calculation, the intense curvature of spacetime near the horizon can separate these fleeting particle pairs. One particle may fall into the black hole, while the other escapes to infinity. To a distant observer, this appears as radiation emitted by the black hole itself, a faint glow arising not from accretion disks or jets, but from the quantum nature of space-time. This is what we now call Hawking radiation. And this idea was shocking. It implied that black holes have a temperature, that they emit radiation, that they lose energy. In short, that they can slowly evaporate. The black hole, long thought to be a perfect absorber, becomes a very inefficient emitter. The temperature of this radiation depends on the mass of the black hole. The larger the black hole, the colder it is. A stellar mass black hole has a temperature far below that of the cosmic background radiation, making its Hawking radiation essentially undetectable. A supermassive black hole is even colder. For all practical purposes, these giants are darker than darkness itself. But for very small black holes, the story changes dramatically. As a black hole loses mass through Hawking radiation, it becomes hotter. As it becomes hotter, it radiates more strongly. This runaway process means that small black holes evaporate faster and faster as they shrink. In theory, a sufficiently small black hole would end its life in a brief but intense burst of radiation. This is a profound shift in perspective. Black holes are no longer eternal fixtures of the universe. They have lifetimes, vast, almost incomprehensibly long lifetimes for large black holes, but finite nonetheless. A supermassive black hole may survive far longer than the current age of the universe, but even it is not truly everlasting. And that's the thing. Hawking radiation introduces a new era of time into black hole physics. It connects gravity to thermodynamics. Black holes obey laws remarkably similar to the laws of heat and entropy. Their surface area behaves like entropy. Their temperature governs radiation. Their evolution follows principles that mirror those of ordinary physical systems. This connection runs deep. The area of a black hole's event horizon never decreases in classical general relativity, much like entropy in an isolated system. Hawking radiation modifies this picture, allowing the horizon to shrink, but only in a way that preserves a generalized form of the second law. The total entropy of the black hole plus its surroundings still increases. Here, black holes stop being exotic exceptions and start looking like part of the broader fabric of physics. They are not anomalies. They are thermodynamic objects. And that realization has enormous consequences because it suggests that space-time itself has microscopic degrees of freedom, something like atoms of geometry. Yet Hawking radiation also brings with it a deep and troubling puzzle. If black holes evaporate completely, what happens to the information about the matter that fell into them? Quantum mechanics insists that information is never destroyed, but if a black hole forms from a pure quantum state and evaporates into thermal radiation, the final state appears to be mixed, random, and devoid of the original information. This is the black hole information paradox. It is not a technical detail. It strikes at the heart of our understanding of reality. Either information is lost, violating quantum mechanics, or our description of black holes is incomplete. For decades, this paradox has fueled intense debate. Some physicists argued that information truly is destroyed, requiring a modification of quantum theory. Others believe that information is somehow encoded in subtle correlations within Hawking radiation, preserved but extraordinarily difficult to reconstruct. Still others propose that information remains on the event horizon itself, stored in microscopic degrees of freedom. What makes this paradox so compelling is that it arises from combining two of our most successful theories, general relativity and quantum mechanics. Each works extraordinarily well in its own domain. Together they produce contradiction. And contradictions in physics are precious. They point the way to deeper understanding. The idea that black holes are not completely black also reshapes our intuition about horizons. The event horizon, once thought to be a one-way membrane with no local properties, acquires thermodynamic significance. It has temperature, it has entropy, it behaves like a physical system. This hints that horizons may be more than mere boundaries. They may be dynamic, information-bearing structures. It is also worth reflecting on the timescales involved. For stellar mass black holes, evaporation times are staggeringly long, far exceeding the current age of the universe. For supermassive black holes, the timescales are so vast that ordinary language begins to fail. These objects will outlive stars, galaxies, perhaps even the era of star formation itself. Hawking radiation matters not because it is fast, but because it is inevitable. In the far future, when the universe has grown cold and dilute, when star formation has ceased and galaxies have faded, black holes may become the dominant engines of change. Slowly, patiently, they will radiate away their mass, converting gravitational energy into particles and light. Even in near emptiness, physics continues. And there is something strangely comforting in that. Nothing is exempt from change, not even black holes. The universe does not create permanent monuments, it creates processes. Hawking radiation also reinforces the idea that black holes sit at the crossroads of physics. They connect gravity, quantum theory, thermodynamics, and information. Any successful theory of quantum gravity must explain black hole evaporation and resolve the information paradox. In this sense, black holes are not just astrophysical curiosities, they are guides. Some speculative ideas suggest that evaporation may leave behind a remnant, a tiny object containing the information of the original black hole. Others propose that space-time itself reorganizes, releasing information in ways we do not yet understand. These ideas remain under active investigation, and none have achieved consensus. What is clear is that Hawking radiation shattered the notion of black holes as perfect absorbers. It revealed that even the darkest regions of space-time participate in quantum processes. It reminded us that emptiness is never truly empty, and boundaries are never truly inert. As we contemplate the slow evaporation of black holes, another question naturally arises. If information is not destroyed, where is it? How is it stored? How does it escape? These questions lead us away from energy and mass, and toward the nature of information itself. To pursue them, we must confront the information paradox head-on. We must ask whether black holes erase history, or merely hide it, whether the universe is fundamentally forgetful or perfectly faithful to its past. And so, having watched black holes fade not with a bang but with a whisper, our attention turns to one of the deepest debates in modern physics, the fate of information in a universe where even the darkest objects are not beyond the reach of quantum law. And so, from the quiet evaporation of black holes, from the whisper of Hawking radiation that hints at impermanence even in the deepest gravity wells, we arrive at a question that cuts straight to the foundations of reality. What happens to information? Not energy, not mass, but information. The detailed record of what fell in, how it was arranged, what it once was. Does the universe remember, or can it truly forget? At first glance, the answer seems simple. A black hole forms. Matter falls in. The event horizon seals shut. Later, the black hole evaporates into a bath of thermal radiation. If that radiation carries no imprint of the original state, then the information is gone. Destroyed. But that conclusion sits uneasily with one of the deepest principles of quantum mechanics. Information is never lost. It may be scrambled, hidden, dispersed, but it is always preserved. This is the black hole information paradox, and it is not merely a technical puzzle. It is a clash between two pillars of modern physics. General relativity, which describes black holes so beautifully, seems to allow information loss. Quantum mechanics, which governs the microscopic world with astonishing accuracy, forbids it. Both theories work extraordinarily well. Both are supported by overwhelming evidence, and yet, when applied together to black holes, they disagree. To appreciate why this matters, we need to understand what physicists mean by information. In this context, information is not meaning or memory in a human sense. It is the complete specification of a physical state, the exact arrangement of particles, their quantum properties, their correlations. If you know the information, you can in principle predict the future evolution of the system. Quantum mechanics is built on the idea that this information is conserved. The evolution of a closed system is reversible in principle. If you know the final state exactly, you can reconstruct the initial state. This reversibility is woven into the mathematics of quantum theory. To abandon it would be to rewrite the rules. But black holes seem to demand exactly that. When matter crosses the event horizon, its information becomes inaccessible to the outside universe. From the outside, all that remains are a few gross properties of the black hole: its mass, its spin, its charge. Everything else appears to vanish. When the black hole evaporates, the radiation looks thermal, random, devoid of structure. Where did the information go? One possibility is that information really is destroyed. That black holes are fundamentally different from all other physical systems. This would require modifying quantum mechanics itself, allowing for non-unitary evolution. Some physicists once favored this view, but it comes at a heavy cost. Quantum mechanics underpins not only particle physics, but chemistry, materials science, and much of modern technology. Changing it would ripple outward, demanding a radical rethinking of physics as a whole. Another possibility is that information is preserved, but in a highly non-obvious way. Perhaps it is encoded in subtle correlations within the Hawking radiation, not in individual particles, but in the relationships between them. In this view, the radiation is not truly random. It only appears so when examined in small pieces. Taken as a whole, it may carry the full record of what fell in. This idea is appealing, but it raises difficult questions. Hawking's original calculation suggested that the radiation is purely thermal, carrying no information. To encode information, the radiation must deviate slightly from perfect thermality. These deviations would be extraordinarily small, especially for large black holes. How, then, could they encode such vast amounts of information? And how could this process be reconciled with the smoothness of space-time at the horizon? Here the event horizon itself comes back into focus. Long regarded as a featureless boundary, it begins to acquire new significance. Some proposals suggest that information is stored on the horizon, spread across its surface like bits on a screen. This idea leads naturally to the holographic principle, one of the most profound insights to emerge from black hole physics. The holographic principle suggests that the information content of a region of space is encoded not in its volume, but on its boundary. In the case of a black hole, the entropy is proportional to the area of the event horizon, not the volume inside. This was a startling discovery. It hinted that the universe may be fundamentally two-dimensional at its deepest level, with the three-dimensional world emerging as an effective description. In this picture, the event horizon is not an empty geometric surface. It is a dynamic, information-rich structure. Every particle that falls in leaves an imprint on the horizon. As the black hole evaporates, that information is gradually released, scrambled but intact. The black hole does not destroy information, it transforms it. And this idea extends far beyond black holes. If the holographic principle is correct, it may apply to space-time itself. Our entire universe could be described by information encoded on a distant boundary. Space and time might be emergent, arising from deeper, more abstract degrees of freedom. But the story does not end there. Attempts to reconcile information preservation with the smoothness of the horizon have led to new paradoxes. One of the most famous is the firewall paradox. If information escapes in Hawking radiation, then late-time radiation must be correlated with early radiation. Quantum mechanics limits how these correlations can be shared. To satisfy all constraints, something has to give. One possibility is that the horizon is not smooth at all. Instead of a gentle crossing, an infalling observer would encounter a searing wall of high-energy particles, a firewall. This would violate the equivalence principle, a cornerstone of general relativity, which says that free-falling observers should experience nothing special at the horizon. The firewall proposal is deeply unsettling. It suggests that one of our most trusted principles fails at the edge of a black hole. Other physicists argue that the paradox signals a flaw in our assumptions, not a literal firewall. Perhaps space-time is more subtle. Perhaps locality breaks down. Perhaps quantum gravity allows correlations that defy our classical intuitions. What is clear is that the information paradox has become a focal point for modern theoretical physics. It has driven progress in string theory, quantum gravity, and our understanding of space-time. In some contexts, particularly in lower dimensional models, researchers have been able to show explicitly how information can be preserved and recovered. These successes provide hope that the paradox will eventually be resolved without sacrificing fundamental principles. And there is something profoundly human about this struggle. We are confronting the limits of knowledge using tools forged in very different regimes. Black holes force us to think about information not as an abstract bookkeeping device, but as a physical entity tied to geometry and gravity. They also force us to reconsider what it means to know something. If information is preserved but irretrievably scrambled, does that count as preservation in any meaningful sense? If the universe remembers, but no observer can ever reconstruct the memory, is that different from forgetting? These questions blur the line between physics and philosophy. They remind us that our theories are not just predictive machines. They are frameworks for understanding existence itself. Black holes sit at the intersection of those frameworks, exposing their tensions and pointing toward their unification. As research continues, the information paradox remains unresolved in its full generality. But it has already taught us something vital: that space-time and information are intimately connected, that gravity may be an emergent phenomenon arising from the organization of information, that the universe is not just made of matter and energy, but of relationships. And so, having followed black holes from stellar death to quantum evaporation, from galactic regulation to informational mystery, we find ourselves drawn back toward observation. Because while theory wrestles with paradoxes, the universe continues to offer clues. Black holes are no longer purely theoretical. They are observed, measured, photographed, and listened to through ripples in space-time. To ground these deep questions, to test our ideas against reality, we must turn to how black holes are actually observed, how their presence is inferred, and how recent technological advances have transformed them from mathematical curiosities into measurable entities. Only by connecting theory with observation can we hope to learn whether the universe truly forgets or whether it remembers everything, written subtly into the fabric of space-time itself. And so, after wandering through paradox and principle, through evaporation and information, we return at last to something grounding, something reassuringly empirical. We return to observation. Because however strange black holes may be in theory, however deeply they challenge our understanding, they are no longer creatures of equations alone. They have stepped, cautiously but unmistakably, into the realm of measurement. And that transition from idea to evidence is one of the most profound moments in modern science. For most of the 20th century, black holes were invisible by definition. They emit no light of their own. They cannot be photographed in any ordinary sense. To many astronomers, this made them deeply suspicious. Science, after all, is built on observation. What cannot be seen, measured, or tested tends to sit uneasily at the edges of acceptance. And yet the universe has a way of revealing its secrets indirectly. The earliest observational hints came not from darkness, but from motion. Astronomers noticed stars moving too fast, orbiting something they could not see. In binary systems, visible stars were whipping around invisible companions with masses far exceeding what neutron stars could plausibly explain. These unseen objects exerted gravity, but offered no light in return. The simplest explanation was a black hole. In galactic centers, the evidence was even more striking. Stars near the cores of galaxies followed tight, rapid orbits around compact regions of immense mass. In our own Milky Way, careful measurements of stellar motions revealed an invisible object with millions of solar masses confined to a region no larger than our solar system. There was no known alternative. A supermassive black hole was the only explanation that fit the data. Still, these were indirect inferences. Convincing, yes, but some skeptics remained. Could there be some exotic cluster of dark objects instead? Some unknown form of matter? Science demands caution, and so the search continued for more definitive signatures. One such signature came from X-ray astronomy. Matter falling toward a black hole heats up, radiating intensely before crossing the horizon. Space-based X-ray telescopes revealed compact sources emitting enormous amounts of high-energy radiation. The variability of this emission, sometimes flickering on timescales of seconds, implied incredibly small emitting regions. Only black holes could concentrate so much energy into so little space. Then came gravitational waves. Einstein had predicted them a century earlier, ripples in space-time produced by accelerating masses. For decades, they remained undetected. And then, suddenly, detectors like LIGO began to hear them. The first signals were unmistakable. They bore the distinctive chirp of two black holes spiraling together and merging, releasing energy equivalent to several suns in a fraction of a second. These detections were revolutionary. They did not rely on light at all. They were direct measurements of space-time dynamics. The masses, spins, and merger rates inferred from these signals matched the predictions of black hole theory with astonishing precision. Black holes were no longer just inferred. They were heard. Each gravitational wave detection added to a growing census of black holes. Some were larger than expected, challenging models of stellar evolution. Others revealed populations of black holes in regions previously inaccessible to electromagnetic observation. The universe, it seemed, was full of black holes, colliding, merging, and reshaping space-time itself. And then, in a moment that felt almost symbolic, black holes were finally imaged. Not directly, of course. What was captured was the silhouette, the shadow cast by a black hole against the glowing backdrop of infalling matter. Using a planet-sized network of radio telescopes known as the Event Horizon Telescope, astronomers combined signals from across the Earth to achieve unprecedented resolution. The result was an image of the supermassive black hole at the center of a distant galaxy, a dark central region surrounded by a bright ring of emission, warped by gravity. The size and shape of the shadow matched theoretical predictions remarkably well. It was not just a triumph of engineering. It was a triumph of decades of theoretical work. And, there was something deeply moving about that image. Not because it was visually dramatic in a conventional sense, but because it represented the first time humanity had seen the immediate environment of an event horizon. A boundary once thought forever beyond reach was now, in some sense, visible. These observations transformed black holes from speculative objects into test beds for fundamental physics. General relativity could be tested in the strong field regime, where space-time curvature is extreme. So far, it has passed every test. The orbits of stars, the shapes of accretion disks, the signals from mergers all align with Einstein's theory to remarkable accuracy. At the same time, these observations have sharpened our questions. Subtle deviations from predictions could hint at new physics. Measurements of spin distributions inform models of black hole formation and growth. The environments around black holes reveal the complex interplay between gravity, magnetism, and plasma physics. Space-based observatories have played a crucial role in this progress. Telescopes operating in X-ray, gamma-ray, and infrared wavelengths have revealed aspects of black holes invisible from the ground. They have traced jets across millions of light-years, mapped hot gas swirling near horizons, and monitored the feeding habits of supermassive black holes across cosmic time. What is particularly striking is how observation and theory now move together. Predictions guide searches. Discoveries refine models. Black holes have become one of the most interdisciplinary subjects in science, connecting astronomy, relativity, quantum theory, and information science. And yet, for all this progress, black holes remain fundamentally indirect objects. We do not see the horizon itself as a surface. We do not observe the interior. We infer. We reconstruct. We listen. This is not a weakness. It is a reminder of how science works. We learn about the unseen by studying its effects. In a sense, black holes have taught us how to observe the unobservable. They have forced us to develop new instruments, new techniques, new ways of thinking. They have expanded the very definition of observation beyond light. As detections accumulate, patterns emerge. Black hole mergers trace the history of stellar populations. Supermassive black hole activity traces the growth of galaxies. Each data point is a fragment of a much larger story, one that spans billions of years and unimaginable distances. And, standing here, at this intersection of evidence and mystery, it becomes clear that observation does not close the book on black holes. It opens new chapters. Each confirmation deepens the puzzle rather than resolving it entirely. Because now that we know black holes exist, now that we have seen their shadows and heard their mergers, the questions shift again. What do they ultimately mean? Not just for galaxies or physics, but for our understanding of reality itself. Black holes force us to confront limits. Limits of measurement, limits of theory, limits of intuition. They hint that space-time may not be fundamental, that information may underlie geometry, that the universe may be far stranger than even our most successful theories suggest. And so, having grounded our journey in observation, we are ready to take one final step beyond it, to ask not just what black holes are and how we see them, but what they imply, about the nature of existence, about possible connections to other universes, to wormholes, to deeper layers of reality still hidden from view. In that final step, physics shades into philosophy, not because the science becomes vague, but because its implications become vast. And it is there, in that space between what we know and what we dare to imagine, that black holes continue to whisper, inviting us to listen more carefully to the universe and to our place within it. And so, having followed black holes from mathematical curiosities to observed cosmic actors, from stellar death to galactic regulation, from evaporation to information, we arrive at a place where the equations begin to blur into questions of meaning. Not because the science becomes weaker here, but because its implications become wider. Black holes, perhaps more than any other object in modern physics, force us to confront what we really mean by reality itself. At their core, black holes challenge the idea that the universe must always be knowable. They present regions where information appears hidden, where observation reaches a hard limit, where prediction gives way to probability and uncertainty. The event horizon is not just a physical boundary, it is an epistemological one. It separates what can be known from what must be inferred, and perhaps from what can never be known at all. This alone would be enough to grant black holes philosophical weight. But the challenge runs deeper. In classical physics, the universe is a machine. Given enough information, the future is determined. Black holes disrupt this picture. They introduce horizons beyond which the classical story breaks down. They invite us to accept that some parts of reality may be permanently inaccessible, not due to technological limitations, but due to the structure of space-time itself. And, that forces a quiet humility upon us. The universe is not obligated to reveal all its secrets. Some of the most speculative ideas in physics grow naturally out of this discomfort. Consider wormholes, solutions to the equations of general relativity that resemble tunnels through space-time, potentially connecting distant regions of the universe, or even different universes altogether. In many models, wormholes are closely related to black holes. A black hole could be one mouth of such a structure, with the other mouth opening elsewhere. Most known wormhole solutions are unstable, or require exotic forms of matter. But their existence in theory suggests that space-time may be far more flexible than our everyday experience implies. If black holes can distort space-time so profoundly that inside and outside lose their familiar meanings, then perhaps connections we now consider impossible are not forbidden by nature, only hidden from view. Then there is the idea of the multiverse. In some theories, especially those involving quantum gravity or cosmic inflation, our universe may be just one of many. Black holes have been proposed as possible gateways to other universes, or even as seeds from which new universes might emerge. In these speculative scenarios, a collapsing region of space-time pinches off, forming a new expanding cosmos beyond the horizon. There is no observational evidence for such ideas, and yet they arise not from fantasy, but from taking our equations seriously and following them where they lead. Black holes, by pushing physics to its limits, open doors to possibilities that feel almost metaphysical. At the same time, black holes challenge our sense of scale and importance. They remind us that the universe operates on timescales and energies far beyond human intuition. A supermassive black hole can outlive stars, galaxies, perhaps even the era of matter itself. And yet, it is governed by the same fundamental laws that describe falling apples and orbiting planets. This continuity is deeply reassuring. It suggests that the universe is not divided into separate realms of the ordinary and the exotic. There is one reality, governed by consistent principles, even if those principles reveal unexpected consequences when pushed to extremes. Black holes also force us to rethink the nature of space and time. Near a horizon, time slows. Inside, time and space exchange roles. The singularity represents a breakdown of classical description, where time may simply end. These features suggest that space and time are not fundamental ingredients of reality, but emergent properties, arising from deeper structures we do not yet fully understand. In recent years, this idea has gained traction. Some approaches to quantum gravity propose that space-time itself emerges from networks of quantum information. In this view, geometry is not primary. Information is. Black holes, with their entropy proportional to surface area and their intimate connection to information paradoxes, become key evidence for this perspective. And that is a radical shift. It suggests that the universe is not made of things, but of relationships. That what we perceive as space is a manifestation of how information is organized. That gravity may not be a fundamental force, but a statistical effect, arising from the tendency of information to spread and entangle. Black holes sit at the center of this transformation in thinking. They are where gravity, thermodynamics, and quantum mechanics intersect most sharply. They expose contradictions. They demand resolution. They guide us toward new conceptual frameworks. Philosophically, black holes also raise questions about determinism and fate. Inside a black hole, the singularity appears inevitable. No choice, no force, no clever maneuver can prevent the inward march of time toward that endpoint. This challenges our intuitive association between the future and openness. In some regions of space-time, the future may be as fixed as the past, and yet, from the outside, black holes evolve. They grow, merge, evaporate. Their horizons expand and shrink. The universe around them changes. This duality between inevitability and dynamism mirrors a tension we feel in our own lives, between the laws that constrain us and the freedom we experience locally. There is also an existential dimension to black holes. They represent ultimate loss. Matter falls in and disappears from view. Information is hidden. Light is trapped. And yet, as we have seen, black holes are not merely destructive. They shape galaxies. They regulate star formation. They convert gravity into light. Even their evaporation contributes energy to the universe. Destruction and creation are not opposites here. They are aspects of the same process. In that sense, black holes echo a recurring theme in cosmology. The universe evolves not through static perfection, but through change, collapse, and transformation. Stars die to seed new stars. Galaxies merge to form larger structures. Black holes form from collapse and may end in radiation. Nothing is final. Everything participates in a larger cycle. This perspective has a quiet emotional resonance. It suggests that even the darkest regions of reality are not meaningless voids, but active participants in cosmic evolution. That endings are also beginnings, even if the connection is hidden from view. Black holes also teach us about the limits of language. Words like inside and outside, before and after, cause and effect lose their clarity near horizons. Our everyday concepts, shaped by weak gravity and slow motion, struggle to describe extreme regimes. This is not a failure of imagination, but a reminder that our minds evolved to navigate a very specific corner of reality. Science allows us to go beyond that corner, but it does not guarantee comfort. Black holes are unsettling because they reveal how contingent our intuitions really are. They show us that reality is not obligated to align with common sense. And perhaps that is their greatest gift. They keep us honest. They prevent complacency. They remind us that understanding is always provisional. As we stand at this philosophical horizon, one final realization emerges. Black holes are not just objects out there in the universe. They are mirrors. They reflect back our assumptions about knowledge, existence, time, and meaning. They force us to ask not only how the universe works, but what it means to understand anything at all. In studying black holes, we are not merely learning about gravity. We are learning about the structure of explanation, about the relationship between theory and observation, about the role of limits in knowledge. And so, as this journey continues, as new observations refine our theories and new ideas challenge our frameworks, black holes remain what they have always been since they first appeared on paper. Not answers, but questions. Not endpoints, but gateways. They stand at the edge of what we know, quietly inviting us forward. And so, without quite realizing it, we step beyond the boundary of black holes themselves and into something even more delicate. Because once you follow these objects all the way to the edge of knowledge, once you let them question space, time, information, and reality, they begin to turn the spotlight back on us, on the observers, on the thinkers, on the fragile, curious creatures who try to make sense of a universe that was never designed to be easily understood. You see, black holes do not merely sit out there, silently sculpting galaxies and bending space-time. They also shape the way we think. They force science to confront its own foundations. They remind us that every theory is provisional, every model an approximation, every explanation a story we tell that happens, for now, to work. There was a time when physics believed it was close to completion, when the laws of nature seemed nearly finished, waiting only for refinement. Black holes shattered that confidence. They exposed contradictions at the heart of our most successful theories. They revealed that general relativity and quantum mechanics, both triumphs of human intellect, speak different languages when faced with extreme gravity. And that realization is deeply unsettling, but also quietly thrilling, because it means the universe still has secrets, not small ones, fundamental ones. Black holes teach us that nature is not obligated to be simple, or intuitive, or even kind to our expectations. They show us that reality can hide behind horizons, that causes and effects can become observer-dependent, that time itself can slow, twist, and perhaps even end. In doing so, they stretch not only space-time, but the human imagination. There is also something profoundly intimate about this. The equations that describe black holes were written by human hands. The ideas that predict their behavior emerged from human minds. And yet, the phenomena themselves are utterly indifferent to us. Black holes do not care whether we understand them. They existed long before the first thought flickered into consciousness, and they will likely persist long after the last observer fades. And yet, here we are, listening, measuring, interpreting faint signals that have traveled for millions or billions of years just to brush against our detectors. That alone is extraordinary. In this sense, black holes highlight a quiet paradox of science. We are both insignificant and essential. Insignificant in scale, in power, in cosmic importance. Essential in interpretation. Without observers, without questions, without minds willing to wrestle with paradox, black holes would simply be. With us, they become part of a story, and, stories matter. They are how humans navigate complexity, how we bridge mathematics and meaning. Black holes also remind us of the importance of limits. In everyday life, limits feel restrictive. In physics, limits are revealing. The speed of light, the uncertainty principle, the event horizon. These are not failures of understanding. They are structural features of reality. Black holes gather many such limits into a single place, making them impossible to ignore. At the event horizon, predictability breaks down. Inside, classical descriptions fail. At the singularity, Our equations surrender entirely. This is not defeat. It is a signpost. It tells us where new ideas are needed. Perhaps quantum gravity will one day resolve these tensions. Perhaps space-time will be shown to emerge from entanglement. Perhaps information will replace geometry as the fundamental currency of reality. Or perhaps something even stranger awaits, something we do not yet have words for. What black holes guarantee is that the journey is not over. They also encourage a kind of intellectual humility that feels increasingly rare. The more we learn, the more we realize how much remains unknown. Black holes sit at the center of that realization. They are objects defined as much by what we cannot see as by what we can measure. And yet, despite all this mystery, black holes are not nihilistic. They do not suggest that knowledge is impossible. Quite the opposite. They show us that knowledge is layered, that understanding deepens not by eliminating mystery, but by refining it. Each generation of physicists inherits the questions left unresolved by the last. Black holes ensure that there will always be such questions. They keep science open-ended. There is also a quiet emotional resonance here. Humans have always been drawn to darkness, to the unknown, to the edge of things. Caves, oceans, night skies. Black holes are the ultimate extension of that fascination. They are darkness with structure, mystery with mathematics, and, perhaps that is why they captivate us so completely. They sit at the intersection of fear and wonder, of destruction and creation, of silence and revelation. In contemplating black holes, we are also contemplating time, not just cosmic time, but our own. Civilizations rise and fall in the blink of a galactic eye. Entire histories unfold while a black hole barely changes. And yet those brief histories are where meaning lives. Black holes remind us that meaning is not proportional to duration. A star may shine for billions of years. A thought may last seconds. Both are real. Both matter in their own contexts. As science advances, black holes will continue to serve as anchors for speculation and rigor alike. They will test new theories, inspire new technologies, demand new mathematics, and quietly, persistently, they will refuse to be fully domesticated by our understanding. And so, standing here at this extended horizon of thought, it becomes clear that black holes are not merely subjects of astrophysics. They are companions in a deeper journey, one that asks not just what exists, but how we come to know it. Not just how the universe behaves, but how explanation itself works. In that sense, black holes do not end stories. They prolong them. They ensure that curiosity survives certainty, that wonder outlives explanation. And as we continue forward, as new observations arrive and new theories take shape, the conversation between humanity and the cosmos goes on, quietly, patiently, always unfinished. Because the universe is not a puzzle meant to be solved once and for all. It is a dialogue, and black holes, silent though they may be, remain among its most compelling voices. And so we come, gently and without finality, to the end of this particular journey, though not to an ending in any true sense. Because black holes, you see, do not offer closure. They do not resolve the universe into something neat and complete. Instead, they leave us suspended in a state of thoughtful imbalance, aware that understanding is always provisional, always unfolding. From the moment the idea of a black hole first appeared as a curious consequence of gravity, to the time we learned to listen to their mergers and glimpse their shadows, these objects have carried a quiet message. The universe is deeper than it looks. Reality is richer than intuition allows. And certainty, however comforting, is rarely the final word. Black holes are often described as destroyers, as cosmic endings where matter, light, and time itself disappear. But if there is one truth that emerges from everything we have explored, it is this. Black holes are not simply agents of destruction. They are engines of transformation. They collapse stars. Yes, but in doing so they seed galaxies. They trap light, yet give rise to some of the brightest phenomena in existence. They hide information, but in hiding it, they force us to rethink the very foundations of physics. In that sense, black holes do not represent absence. They represent concentration, an intensity of gravity, an intensity of curvature, an intensity of unanswered questions. And perhaps that is why they resonate so deeply with us. Because in a universe that can feel overwhelmingly vast and indifferent, black holes are places where everything matters, where every assumption is tested, where the rules we rely on are pushed to their breaking point. They remind us that space is not an empty stage, but an active participant. That time is not a universal river flowing evenly for all, but a landscape shaped by motion and mass. That information, once thought abstract, may be as physical as energy or matter. These are not small revisions. They are shifts in worldview. What is particularly humbling is how these revelations arise, not from speculation alone, but from disciplined curiosity, from equations written on paper, from telescopes assembled atom by atom, from detectors sensitive enough to feel space-time itself tremble, human hands and human minds reaching outward, guided by wonder rather than certainty. And yet, for all our progress, black holes remain stubbornly resistant to complete understanding. We can describe their exteriors with extraordinary precision. We can predict their mergers. We can measure their masses and spins. But the interior, the singularity, the ultimate fate of information, these remain open questions, not because we have failed, but because nature has not yet yielded those answers. This is not a flaw in science. It is its lifeblood. Black holes teach us that mystery is not an enemy of knowledge. It is its engine. Every unresolved paradox points toward deeper structure. Every contradiction signals an opportunity to grow beyond our current frameworks. In this way, black holes serve as guides, not obstacles, on the path of understanding. They also invite us to rethink our place in the universe. Compared to a black hole, we are fragile, fleeting arrangements of matter. Our lives unfold in moments, while these objects persist across cosmic epochs. And yet, it is we who ask the questions, we who listen, we who seek patterns in the dark. That alone is extraordinary. There is a quiet poetry in the fact that beings made of stardust can comprehend the death of stars, that creatures bound to a small planet can reason about space-time on galactic scales. Black holes make this contrast impossible to ignore. They dwarf us physically, yet they elevate us intellectually. And perhaps they also offer a lesson in humility. Black holes do not bend to our desires for simplicity or comfort. They do not provide easy metaphors or tidy conclusions. They exist on their own terms. To understand them, we must adapt our thinking, not the other way around. This humility extends beyond physics. It touches philosophy. It touches how we think about knowledge itself. Black holes show us that some truths may always be indirect, inferred rather than observed, known through effects rather than essence. That does not make them less real. It makes them more subtle. They also blur the boundary between science and meaning. When we ask what happens inside a black hole, we are not only asking about equations. We are asking about causality, about determinism, about whether the universe remembers its past. These are questions that echo far beyond astrophysics. And still, black holes are not bleak. They are not symbols of cosmic despair. If anything, they are reminders of continuity. Matter falls in, but energy reemerges. Stars die, but galaxies evolve. Even black holes themselves may one day fade, dissolving slowly into radiation. Nothing stands outside the flow of change. In this way, black holes align with a deeper truth about the universe. There are no absolute endings, only transformations. As we look ahead, it is clear that black holes will remain central to the story of science. Future observatories will map their environments in greater detail. Gravitational wave detectors will listen to ever more distant mergers. Theories of quantum gravity will continue to be tested against their demanding constraints. Each advance will answer some questions and raise others. And that is exactly as it should be, because the universe is not a puzzle with a final solution waiting to be uncovered. It is an evolving conversation between reality and those who seek to understand it. Black holes ensure that this conversation remains rich, challenging, and alive. They remind us that knowledge is not a destination, but a journey. That understanding grows not by eliminating darkness, but by learning how to navigate within it. That curiosity, sustained over generations, is one of the most powerful forces in the cosmos. So when we think of black holes, perhaps we should not think only of what they take away. We should think of what they give. They give us perspective. They give us questions worthy of our best efforts. They give us a reason to keep looking, listening, and wondering. And in the end, that may be their greatest legacy. Not the collapse of stars, not the bending of space-time, but the way they quietly insist that the universe is deeper than we imagine, and that our desire to understand it is, in its own small way, part of the same cosmic story. The darkness, it turns out, is not empty. It is full of meaning.